In this video, I will demonstrate the SAP1 architecture-based 6-bit computer design and implementation project from Tripoli 4308. Here in this Proteus simulation, we have defined integrated types of modules with a 6-bit bus. At first, we have a clock pulse module, which will pulse from 1 to 0. And then we have a program counter which can count from 000 up to 111 as it is a 3-bit program counter. And below that, here we have a address selector which will select input from input unit and memory address register and give the output to the RAM and give the output to the RAM. And below that, here we have instruction register and control sequencer. In the instruction register, it will store the 6-bit instruction from the RAM. And below that, we have a control sequencer which will control the other modules by bringing some signals. And then if we see here, we have a B register where the data will be stored and the arithmetic logic unit will process the data by adding or subtracting. Below that, if we see, we have a output register which will give the output in binary values, and in the and after that we have added a 7 segment display which will take the binary output and show the output in decimal value. Now let us add two numbers. To do that, we have to simulate the whole thing, for which we turn off the clock pulse and then we simulate our Proteus simulation. And now we can see that here we have a read write option and the run program option, and then we have 3 other numbers, and then we have 6 numbers. So to do a addition operation, firstly, so we give 1 here and we keep 0 here and we keep 0 here. Here in the 6-bit number, the first 3-bit denotes the opcode and the next 3-bit denotes the address. So I am going to give the address to 5, that is 101. Now we give read write here, that is 01 here, and we take here the 1 position. After that we take the opcode to 001 and give the address to 6, that is 110. Then we read write again and we select here 10 and we give the opcode to 011 and deselect the address as it is an output. Now we give read write, that is 01 and select 011 and give the opcode to halt. Then we read write the whole thing again and give the address selection and give the opcode to 000 and the address selection 11, and in this part we give 101. Now we read write the whole thing and go to the 6th position and again give the input to 11. Now we give read write again. Now what we have done is added 3 plus 3, and now we are going to run the program and select here run and all the values to 0. Now we have to select here that is on the clock pulse, and by doing that we get our desired output, that is 3 plus 3 6. Now similarly we can simulate subtraction of any values of 6 bit by giving the values here and the opcode required for subtraction. Now let me show you how we design different components in our SAP. So let me start with the control sequencer and go to the child sheet. Here we can see 12 bit in the control sequencer, which will going to control the entire SAP1, and these control bits are recognized by using opcodes, and the opcodes are 5 in number, so we use 5 JK flip-flops here. Here we have a reset program by which we can terminate the uh, present program and start a new program. And here for 12 different bits we get 12 different sorry for 12 different control bits we get 12 different outputs. As in our 6-bit SAP, each of the component are of 6 bit, where the first 3 bit are called the opcode, which defines the instructions the component has to do, which are loading the data, addition, subtraction, output, and halt. The next 3 bit passes the address field in the instruction, and control bits are unchanged in the T state. So let me introduce you to our next component, which I'm going to describe, the ALU. So we go to the child sheet. Here we have designed to add two numbers and subtract two numbers, such that we can input two numbers and those two numbers are to be added or subtracted according to the controls we give it. So let me go to the uh, parent sheet and continue from there. Here in our ALU, if we here we can see there are two control bits which are SU and EO. SU is the addition subtraction unit of the SAP1. When SU is 0, addition is done, and when SU is 1, subtraction is done. Here, the EO puts the output from ALU onto the bus if the RAM output or are low. If RAM output is 0, output is disconnected from the bus. Then we can talk about our instruction register, which have 6 inputs and 6 output. An input 3 bit moves to the control sequencer. The rest of the 3 bits are passed to the bus memory. Here we see IIIO, clock and reset. If II is enabled, this takes 6-bit data from the bus, of which 3 bits are for instruction and the rest of the 3 bits are for is enabled. This sends 3-bit data to bus. And our instruction register is designed using, let us go to the child sheet. the IC 748C173. And now we can go to the child sheet, parent sheet, and look at the output register, which take the 6-bit in 6-bit data and output it to the and output the 6-bit binary data, which is again sent to the second 7 segment display, where the binary data is converted into decimal data and showed to the screen. So this is our SAP1, and I hope you really loved our design. Assalamu alaikum. Uh, this is Faimunubi Tarango describing our SAP1 from Electrobits.